Thank you for the invitation to come here. So we'll talk about the Broglie-Bohm approach to quantum cosmology. So let us begin to present the Broglie-Bohm quantum theory. And I use the words of John Bell, which goes straight to the point. And so he says, well, the kinematics of the world in this orthodox picture, which is usually known as the Copenhagen interpretation, is given by a wave function for the quantum part and classical variables which have values in the sense that they have objective reality, they are real, for the classical part, so the psi and the x. The x are somehow macroscopic. This is not spelled out very explicitly. The dynamics is not very precisely formulated either. It includes a Schrödinger equation for the quantum part and some sort of classical mechanics for the classical part, and collapse recites for their interaction. It seems to me that the only hope for precision with the dual psi-x kinematics is to omit completely the shift split and let both psi and x refer to the world as a whole. Then the x must not be confined to some vehicle macroscopic scale, but must extend to all scales. So he's saying that in order to describe a quantum system, you need not only the wave function, but also, in the case of the non-relativistic particles, the position. In the case of fields, the amplitude of the fields. So, these two variables are important. So in non-relativistic particles, we have the Schrödinger equation for psi, so it should have some equation for x also. And this was done first by the Broglie in 27, but then Bohm ameliorated it in 25 years afterwards. And the situation is like this. So we have the Schrödinger equation for psi, and the equation they propose for x, in the case of non-relativistic quantum mechanics, is just equating the momentum to the gradient of the phase. The S here is the phase of the wave function. So just to resemble to the Hamilton-Jacobi theory. So these are the guidance relations which allows the determination of the trajectories of the particles. Now, so we give an initial wave function, and then the Schrödinger equation will give what is the wave function at all times. Then you get the phase, then you come here, and then you integrate it and get the trajectories, but this will depend on the initial position. And the initial position is the hidden variable of the theory, because once you try to know the initial position, then you perturb the system and you don't know anymore what's going on. You go to another system. So, in order to understand better this, so let us write the wave function in this polar form. Then we have here, if you put this in the Schrödinger equation, we have these two equations. And this is like the Hamilton-Jacobi equation, but with an extra term here, which is so-called quantum potential. When this becomes negligible, then the S is just the Hamilton-Jacobi classical action, where we put here, we recover the classical trajectory. And this equation here is just a continuity equation. Now, as I said, the initial position is unknown. Now, suppose you have an initial distribution of initial positions. So we have a distribution of initial positions at some time, t equals 0. And suppose that it's exactly psi square at this time. Then because of these two equations, then the distribution of positions at any subsequent time would be psi square at this subsequent time, and all the statistical predictions of quantum mechanics are recovered. However, there is something stronger than that, which was first proved by Valentini and developed by many others. Suppose that the distribution of initial positions of the particles is not exactly psi square, but obeys some just continuity requirements and all these things. So they show that because of this equation and this equation here, this distribution here relates rapidly to psi square in a cross-gradient sense. So in this sense, so this is the so-called quantum wave theorem, and as he said, they go to quantum mechanical equilibrium. So quantum mechanical equilibrium is when the the initial arbitrary distribution goes to psi square. And once it goes to psi square, it stays in psi square because this is preserved by these two equations. So in this formulation, the Born rule can be obtained and not postulated. what it can say is about the measurement problem. As you know, the coherence can explain why you do not see macroscopic interference, but it does not explain the unicity effects. For instance, in the famous experiment of the dead or alive cat, the wave function bifurcated in two branches, dead and alive. They do not interfere because of decoherence, but you do not understand and not know why, in the end, you see only one of these possibilities. So for the unique fact, we need to postulate a collapse. It must be postulated because there's nothing to distinguish this branch to the other. However, in the Broglie-Bohm theory, we have something that's real, which is the positioning configuration space. Note that the configuration space here describes everything, the cat, the observer, and everything that you want to put in the problem. So, and here is the point in configuration space. Now, the wave function continues to bifurcate in these two branches, but the point in configuration space has a trajectory, and you get one of these two branches, depending on the initial position that we don't know. So when you get one of these branches, then this branch is selected with respect to the other. There is an asymmetry here. And everything that is done in this branch will never be affected by this other branch because of the coherence. So this other branch is completely nothing for here. And then you don't really need to postulate a collapse. You can think that the wave function is always there, there's no collapse, the wave function always satisfies the Schrödinger equation, and you have some kind of effective collapse. So that's the way it solves the measurement problem. Now, some remarks. So the quantum potential is highly non-local, and if the state is, if there is entanglement. And so Bell's inequalities are violated, like in usual quantum mechanics, and it offers a simple characterization of the classical limit, which happens when K becomes negligible. Probabilities are not fundamental in this theory. This is very important. It is a derived concept. And the unknown variable is the initial position. It's a theory with objective reality, but with the same statistical prediction of standard quantum theory. And it has one postulate more, which is the existence of the particle trajectory, we law for it, but it has also two postulates less. You don't need a collapse postulate, and you don't need the Born rule. So in the end, it has -1 postulate in the standard quantum theory. So this is an example of calculation of trajectories in the two-slit experiment. You see, these are the trajectories, and you see the pattern of interference here. And the first time I saw it was very astonished, because I studied quantum mechanics and everybody said, well, the two-slit experiment shows that you cannot even think about trajectories. You cannot even think about trajectories. Well, but and I saw, well, there's an example where you can think about trajectories. Maybe they are not there, maybe they are not real, maybe they are wrong, but maybe you can think about it. So it's not impossible to think about trajectories. And so this was also an astonishment by Bell also, and he says like this. In 1952 is when Bohm developed the theory of de Broglie and published his papers. In 1952, I saw the impossible done. It was in the papers by David Bohm. The subjectivity of the orthodox version, the necessary reference to the observer, could be eliminated. But why then Bohm not told me of this pilot wave, if only to point out what was wrong with it? Why did von Neumann not consider it? Why is the pilot wave picture ignored in textbooks? Should it not be taught not as the only way? I'm claiming that's the only way. Not as the only way, but as an antidote to the prevailing complacency, to show us that vagueness, subjectivity, and indeterminism are not forced on us by experimental facts, but by deliberate theoretical choice. I think that's a very strong statement. Okay, let me move then to apply this to the wave function of the universe and see what you can say about this. So let us talk about the wave function of the universe. So suppose you have Hamiltonian for the universe. So the usual Hamiltonian can be anything you want, but let us take just canonical general relativity. So H is the metric, pH is the momentum canonical conjugate of the metric. Phi describes matter fields, by phi the momentum. So in the Hamiltonian, from Hamiltonian we can obtain the evolution in some parameterized time. And then we proceed with Dirac quantization or some other quantization that we wish. And then we obtain, in this case, if we apply the Dirac quantization, we obtain the Rudolph equation and momentum constant equation. And once we solve for psi, then we can find what is the phase. And using the Broglie-Bohm theory, you can find out what is the evolution of the metric and the matter fields in this context. And of course, if this S here is not exactly the usual Hamiltonian function, then this evolution will not be the classical one. So if you see this equation here, and you see what's going on here, so some people advocated some 10 years ago, like Goldstein and others, that if you see these equations here from here, you can understand that psi is a nomological thing. It's something that gives the laws of motion, exactly like a Hamiltonian or a Lagrangian. Psi is something that gives the law that will guide the fields and geometry of the universe. So, so what you are advocating is that the wave function of the universe is nomological. It's law-like. It gives the law from which the fields will propagate. It's not at all about probabilities. The wave function of the universe is not about probabilities. And it's quite sensible, because you are talking about a single system. What's the sense about talking about probabilities if you have only a single system? How can you test it? So no need to seek for a probability measure. It's natural that the equation for the wave function of the universe does not involve time solving the Rudolph equation, or any other equation for quantum cosmology, for instance, does not involve time. It's natural because this is a nomological, the wave function gives the law, and from it we obtain perhaps an emergent time after we solve it. The only thing that's disturbing is that we expect that there is only one law in the nature. So, and the Rudolph equation or any other equation is an equation for there are many solutions. So, in this, if you want to interpret in this way, I think it's very important to have some boundary conditions which specify the wave function, but unfortunately we don't have. Now, how probabilities arise Well, they arise, as it should, in subsystems contained in the universe. So, these formalisms allow us to define what's the so-called conditional wave function. So let us take an example. So suppose that there are only two fields in the universe, phi 1 and phi 2, and this is the wave function of the universe. Now, suppose one gets the Bohmian trajectory for phi 1, and then you get phi 1 of t. Then you can define the conditional wave function by just plugging this solution here. Then you have a function which depends only on phi 2 and this time parameter. And when you put back in the equation which governs psi, you can find out that under certain conditions, the original equation for psi becomes a Schrödinger equation for psi c with a explicit time appearing there. And as a Schrödinger equation appears, then you can invoke the quantum equilibrium, and then you can understand the norm of psi c squared as a probability measure for this subsystem. And as you may have many subsystems in the universe, then this probability can be tested as it should. Okay? So I don't know if someone... Oh, let me continue because I have a lot of things to do. So let us apply this to cosmology and many problems in cosmology. So the first problem, which I think is very important, and very, very important, is the problem of the quantum to classical transition in the theory of cosmological perturbations, which is, I think it's a very important problem which is not really very well addressed. So this is the line element. So here is the scale factor. This is the phi, the perturbation, which is the inhomogeneous perturbations related to Newtonian rotation in the non-relativity limit. Suppose also you have delta phi with the perturbation of a scalar field. Okay, so this is the geometry. So it's Friedman geometry plus perturbations. So a very suitable variable to describe the evolution of perturbations is the Mukhanov-Zak variable, which is just a combination of phi and delta phi, and is related to the curvature perturbation in this way. I will define this function of the background as phi prime over h. Prime is the relative respect to conformal time. It's here. Okay. So it's the background variable. Now, from general relativity, you obtain the Lagrangian for this variable here, this Mukhanov-Zak variable, which is this one here. It depends on the background in this way. And the equations of motions for the modes are this one here. Cs square is the fluid velocity, if there is one. It can be 1 or less than 1. Okay. Now, let us quantize it. Now, if as it is a linear perturbation theory, then you can separate the wave function in the product of functions of each mode, wave functions for each mode. For each mode, and then you can show that this function for each mode satisfies this Schrödinger equation here. So for the modes, and the vacuum state, if you want, the vacuum state is this function here, which satisfies this equation. This fk here, this f of k here, must satisfy this equation here, which is exactly the classical equation for the perturbations. And in the situation where this term here is much bigger than this term here is the term which has the dynamic of the background. And if this term is much bigger than this, or in other words, if the dynamics of the background is negligible, then you have just a simple harmonic oscillator. And in this situation, in order to have a vacuum state, I will say that the initial condition, the conditions in this situation should be that f of k should have this form, and then you just check that if you put this here, you just have the wave function for the harmonic oscillator, the ground state of the harmonic oscillator, which is a Gaussian, and together with this thing here. Okay. So that's it. So that's the wave function. Now, that's the problem. Well, the vacuum state is homogeneous and isotropic. And so the mean value of V should be 0. The mean value of V squared is also translational invariant. It doesn't depend of if you evaluate this in x or x plus delta, as you can easily see here. This t is the translation operator. More than that, when you calculate the temperature fluctuations in the CMB, the cosmic microwave background radiation, you can expand in the harmonic spherics and the spherical harmonics. And this alpha LM here are related to this psi here is just the same as phi in almost all situations, the same as phi that I defined below, before. And so, but what do I put here? What do I put? I'm sorry. What do I put here? I put what? The mean value of phi, which is 0. I cannot. I put a realization. What is the thing that I put here? Well, there are attempts to solving this problem, and one attempt is by saying that when the universe evolves, the vacuum gets squeezed and squeezed, and it yields a positive Wigner distribution in phase space, which is a quantum distribution which looks like classical stochastic distribution of realization of the universe with different inhomogeneous configurations. So the coherence avoids interference among realizations. and the universe, so you have a lot of this universe with different homogeneous configurations. However, this does not solve the problem at all. Is the same problem of the measurement problem now in the cosmological terms. And the solution was severely criticized by Light, Lieder, Mukhanov, Sudarsky, Weinberg. Why? Because whatever happened, the state is still homogeneous and isotropic. Second, what is the environment of the perturbation in the universe? There's a lot of discussion about that. There's not an answer that everybody agrees. Third, in the Copenhagen interpretation, standard interpretations, different potentialities are not realities. How one of the potentialities become our real universe. So this is the same thing as before. This is the measurement problem here. And so what makes the role of a measurement in the real universe? We cannot, us, as human beings, cannot collapse the wave function because we cannot exist without stars. So this is a very serious problem. It appears in textbooks, people mentioning this problem. And how did the Broglie-Bohm, what's the Broglie-Bohm solution? Well, the existence of an actual field configuration breaks the translational rotational invariance in the same way that the existence of particle trajectory and configuration space breaks the symmetry between these two branches here. So, and the equations for the perturbations are Schrödinger equations. So, the distribution must satisfy the Born rule. And also, there is these guidance equations. The guidance equations, so you have the wave function. This is ground state wave function, evolving. The guidance equations in this situation are given by this thing here. Note that there's an extra term here because the Lagrangian has also this term here. Okay? And if you put the phase of the wave function here, we can solve for V, and V is related to the classical solution in this way. Okay, so F is the classical solution and V is the quantum one. The Bohmian trajectory is here, and here is the classical trajectory. And so let us see what happens with it. Now, this is the equation, and F is the classical solution, and V is the Bohmian trajectory. So let us first think about the situation where k squared is much bigger than z2 prime over z, or in other words, when the physical wavelength of the perturbation is much smaller than the Hubble radius. Now, in this situation, the solution for F is just this complex exponential here, and this happens only when eta is very, very big, so this is just a small correction. And as V is given by this, then it has this form, and it's completely different from here. So in this situation, you are really in the quantum dynamics. So the propagation of perturbation is really quantum here. They're either in the beginning of inflation or in the beginning of a bouncing model. Now, when k squared is much smaller than z2 prime over z, or if the physical wavelength is much bigger than the Hubble radius, so the perturbation is really feeling the expansion of the universe, or the contraction of the universe, then the F is given by some power law. There is one power law that dominates, which is the so-called growing mode, and in the end, F is just proportional to the conformal time times an exponent. And then you substitute this here, then you just find that V will just be proportional to F. So the evolution of V will be exactly equal to the classical one. So you get the classical limit. So I think this is a very nice example on the application of the Broglie-Bohm quantum theory to cosmology, where you can explain conceptually and quantitatively how we get from quantum evolution of perturbations to classical evolution of perturbations, which is a very important point. Now let me continue and then now try to discuss quantum cosmological perturbations in quantum backgrounds. Again, this is the metric. I will just work with the scalar fields with a potential, okay? Z squared now will be equal 1. Then when you calculate the Hamiltonian for the system, the Hamiltonian contains a constraint which depends only on the background variables and a constraint which depends on the perturbation and the background variables. So the Wheeler-Dewitt equation, or the loop quantum cosmology equations, will must annihilate psi, and I will assume that psi can be separated in this way. There is a background psi 0, and a psi 2 which depends on V in this way. Now, if you plug this into the equation here, at 0 order, we have H0 psi 0 equals 0, and then you can solve for psi 0, and then you get the phase, and by using the guidance relations, remember alpha is log of A, alpha here is log of A, and by using the guidance relations, you can integrate alpha and phi to obtain what is alpha and what is phi. But for this, you have to have the psi 0. One example for this that we did in the year 2000 is just a scalar field without potential, V equals 0. Then you have calculated the Bohmian trajectories, and they are here, and then they are contracting from, they are collapsing, contracting classically. This is the classical behavior, and then it should go to the singularity, but then there is a bounce caused by quantum effects, this quantum potential, and then then you have the expanding phase, which turns out to be classical again. So it's very similar to what people with quantum cosmology has obtained afterwards. Very, very similar, right? So we have, for the background, in the situation, we have a bounce. Now I want to make a remark about this. No, this solution is for zero potential. But I will show afterwards a solution with an exponential potential. Okay? It's for zero potential. Now, just a remark about bounce as well. Bouncing models has many good features. First, by construction, solve the singularity problem. And in a bouncing model, simply, you don't have any horizon puzzle, any flatness puzzle, and you can have a framework in order to give reason or a physical reason for the origin of cosmological perturbations. They should arise as quantum vacuum fluctuations evolving in a matter-dominated contracting phase, which yields almost scalar spectral scalar perturbation, as we will see. But this is but why is that? Why bounces can give that? So let me try to show a little bit about this figure, but I think this is very intuitive. So this is log of A, and this can be either log of the Hubble radius or either log of the physical wavelengths of the perturbations. The Hubble radius is just defined as one of the Hubble parameter, and the physical wavelength is A times the comoving wavelength, or A over Q. So in the usual cosmological scenario, so the log of physics goes in this way. So now the perturbations of cosmological interest are, of course, must be smaller than the Hubble radius. If not, you wouldn't see it. But if you go to the past, these wavelengths were much bigger than the Hubble radius, and if there is no bounce or nothing else, then it should always be bigger than the Hubble radius, and then you wouldn't have any kind of theory that could explain why the spectrum is this way or it's not the other way. Now, if you have a bounce, then this can be reflected, and then we go in this way, okay? And then again, in the far past, the wavelengths of the perturbations become again smaller than the Hubble radius. And in this way, when the universe was very big and almost flat, And then you can use quantum field theory in flat space-time to give the initial conditions, which are the vacuum initial conditions that I showed you. And then you can evolve everything to find what is the spectrum of the perturbations around here. This is possible for bouncing models. So one thing that I want to make a remark is that when you have a bounce, inflation is really not necessary. Inflation is very important if you think that the universe had a beginning, if there was a beginning of time. If there was a beginning of time, then inflation is really very important, because if there was a beginning of time, all these problems are there, and then inflation is necessary. But in a bounce, inflation is not really necessary. So you don't need to have inflationary phase here. You can have, but you don't need it. Just this remark that I would like to make. So now let us continue. So let's go to second order to see what happens with the perturbations. Let us to do this first. We construct the conditional wave function, which is what? So we take the psi2 and just substitute here the Bohmian trajectory that you have obtained before, and then you have a wave function, a conditional wave function depends only on the perturbation and the time parameter, which is the conformal time. Then we use the background Bohmian trajectory in order to define a conformal time derivative, because in the equations for psi2 there is one term like this, which gives this term here. And if you substitute here the guidance relations here, we have this, and this is just the time derivative with respect to conformal time. Then, after doing this and after some manipulations, we get exactly the same equation as before, with the difference that now the z is calculated from the quantum Bohmian trajectory, not anymore from the classical ones. So this is the equation. It has the same form as the equations for the classical for classical background, but the difference is that the z, it has the same form. The z is now calculated from the quantum Bohmian trajectory. Just a remark, because this will be important afterwards. For gravitational waves, cs squared is equal 1, and have to substitute this variable here, v, but these other variables here, which is a times the amplitude of the tensor perturbation. And in the equation here, z is substituted by the scale factor. Okay, these are the equations, and then if we impose that in the far past, when the universe was very big, the perturbations were just quantum vacuum fluctuations, then you can evolve everything. We have this z to prime z because you solve for the background, which was the bounce background. And then what we obtain is that the spectral index depends on this w here. What is this w? This w, because the wavelengths will become equal to the Hubble radius at some point, and at this point we have a ratio between the pressure and the energy density of matter in the universe, which is this w, and the w here, which appears here in these two things. So if you want to have a normal scale invariant spectrum, then this w should be 0. So when the scales of cosmological interest cross the Hubble radius, then the universe should be dominated by some non-relativist fluids, perhaps dark matter, and then you have scale invariant. Note that it's not necessary to have ordinary matter dominating all along, just at the moment when perturbations with Wilson scale becomes comparable with the Hubble radius. Okay, so but there are some challenges. First, with a single canonical scalar field within general relativity, bouncing models, I'm talking about bouncing models, with a single canonical scalar field within general relativity, including classical extensions of it, the ratio of the tensor perturbations over scalar perturbations is bigger than 0.1. but observation says that this ratio should be less than 0.5. There is also a second challenge, which is very important, and sometimes people forget about it, but it's very important. Dark energy may be very important in the contracting phase. Know that dark energy dominates when the universe is very big. So if you are putting initial conditions when the universe was very big in the past, so dark energy must be important there also. But the problem is that dark energy makes it very difficult to impose vacuum initial conditions in the far past of the contracting phase. Why? Because, well, if you have a normal fluid, the A is essentially proportional to some t, this cosmic time here. So to some power, alpha, this alpha is less than 1, and RA is proportional to T, always proportional to T in this situation, for a fluid satisfying the strong energy condition. So in this situation, the wavelengths will always, in the past, will always be smaller than the Hubble radius. Then we can impose this vacuum initial condition and everything goes right. But if you have dark energy, then the Hubble rays become a constant. Then you have a problem, because then these things go, the Hubble rays goes in this way, and then again, the wavelength of the physical wavelength of the perturbations will become bigger than the Hubble radius. So even if you put initial conditions here, and if you go back to the past, when the physical wavelengths become bigger than the Hubble radius, then there will be a growing mode, and then you might have perturbation exploding in the past, and the model may be unstable. So this is a very important problem that sometimes people don't think about it, but it's very important. What happens with dark energy in a bouncing model? So I'll try to, with a simple example, to propose a way to solve these problems. Okay? And this is the last part of my talk, the last subject, with the scalar field with exponential potential. Okay? And let us see what happens here and how we can solve these problems that I'm telling you. So now I have a scalar field, exponential potential, like this. It's well known that the exponential potential has an attractor, and this attractor is given by the ratio between the pressure and the energy density of the scalar field. It becomes a constant, that becomes a constant, and this constant is related to this lambda here through this equation here. And because of the result that we should have a long contraction matter dominated, I will choose that lambda should be square root of 3 in order to have W equals 0 here. Now, I'm sorry, this is, I don't know what happened here. So, defining this variable x and y, I is essentially the Hubble radius divided by square root of the potential. That's essentially proportional to the Hubble radius. So, the Friedmann equation can be written in this way. So, everything will happen in this circle here. And the other equation, well, I choose the evolution in terms of alpha of log of A, is given by this here. So this is y and this is x. So y positive means expansion, y negative means contraction. There are these critical points. You can read from here very easily. There are these critical points here. This critical point here, x plus or minus 1 and y equals 0, are the singularities. So this half part is completely disconnected from this part here, because this point here is a singularity. These 2 points here are singularities. And these 2 points here are here the attractor and here the repeller, which is the situation where the scalar field behaves as dark matter. So, what are the possible classical solutions? So, in the expanding phase, so there's a possibility that the universe rises here from a singularity, and it expands till we get here, the attractor. Then the scalar field here behaves as dark matter. Note that here the scalar field behaves. So here is x equal 1. So W equal 1. So here the scalar field behaves as stiff matter, indicating that when you approach the singularity, the potential is negligible compared to the kinetic term. But you can also have another possibility, which is the universe begin here, then it expands, then here it passes by a phase which is x equals 0, where W equals minus 1. So this same scalar field behaves here as dark energy. And then it goes again to this attractor line. For the contracting phase, it's more or less the same, but in the reverse. The universe begins contracting from dust, dark matter, W equals 0, and then it goes to the singularity by here. Or we can contract from W equals 0, passes through a phase of dark energy, and then goes to the singularity. Now, this is the classical picture. Now we want to quantize it. And if there is a bounce, what should happen here? Well, if there is a bounce, the bounce will happen around the singularity. And around the singularity, we saw that the potential is negligible. So we can use the result that we had before, that the bounce happens in this way. After we show that this is indeed correct, even if you take the potential, the full potential in the calculations. So, but now look how the bounce is. The bounce it comes from here, and this is the phi d alpha. This is alpha, and this is phi, alpha and phi. So if you go by here, so alpha is equal phi, so x is equal 1. So you are more or less around here. So it makes the bounce, and then you have this trajectory here, and then x is equal minus 1. So if you have a bounce, then when you are approaching this singularity, then you must emerge here. And if you reverse time here, you can do it. You have the same situation. If you're approaching the singularity by here, then you must emerge here. Must be like that. Cannot be the other way around. Must be like that. So what I'm telling you is that if there is a bounce, you have either this possibility here, and then a bounce and goes here, or this possibility, you have a bounce and goes here. So either there is dark energy in the expanding phase or in the contracting phase, but never in both. So you choose the situation where the dark energy is appearing in the expanding phase. The solutions are necessarily asymmetric, and as I said, I will choose this possibility here. And in fact, we have, well, I don't know if we have much time, but we have calculated everything using the potential. So this should be because you have to use other variables, then this is the classical solution. Contraction goes to singularity, this expanding phase, coming from singularity, and then I have shown that there is this bounce here, considering the whole theory, including the exponential potential. Now, you calculate the perturbations on it, and this is very nice. Now, you calculate the perturbations, so here is the curvature perturbation, which is related to V in this way, and here's the tensor perturbation, okay, which is related to V in this way. So what will we obtain? So what we have here, well, when the perturbations are inside the Hubble radius, they oscillate, right? They oscillate, and then they enter the Hubble radius, and then they are amplified. And note that they are amplified. This is the real part and imaginary part of both things, okay? So they increase in the same way, but here near the bounce there is a difference in what happens with the scalar perturbations and the tensor perturbations. You see that near the bounce, where quantum effects become important, the scalar perturbation become much bigger than the tensor perturbation by 4 orders of magnitude. And why this happens? This happens because what makes amplification is this integral here for the scalar perturbation, and is this integral here for tensor perturbations. Now, if you are strictly in the general relativity, the x is close to 1, and so both go in the same way. But if in the bounds quantum effects become important, then x is not anymore restricted to B1. And in fact, if you have a very profound bounce like this, a very steep bounce like this, then the alpha phi is very big, so phi the alpha, which is x, becomes very small, and then you have an enhancement of perturbation here. So in this situation, you have an amplification of scalar perturbations over tensor perturbations, which makes R much less than 0.1. The amplitude is nice because there is this, you have to multiply all these things here by 10 to the minus 6 because there is L Planck of rubber radius today multiplying everything, so Z squared 10 to the minus 10. Remember that it comes from a contraction which is dominated most of the time by a W equals 0 equation of state. So the spectral index is equal to 1, and so
and it's natural for W to be negative as well.
What?
It's also natural for W to be slightly negative.
Yeah, because W will be negative only when the expanding phase in this bond, in this kind of bond, only the expanding phase. That was what I was trying to explain here. I'm taking this model here. So the scalar field behaves like dark matter here, and goes to stiff matter, and then there's the bounce. Here, there's a dark energy behavior in the expanding phase. Okay? And what I'm showing here is what happens before the bounce, then in the bounce, and then after the bounce, then it continues. Then there will be a lot of things, creation of structure and all these things. Okay? So, just with one fluid in a single shot, you could accommodate the matter contraction necessary in bouncing models and a dark energy phase which does not contract quantum vacuum initial conditions. So the quantum bounce was fundamental for that, not only through the connection between the contracting and expanding phase, but also because the quantum effects can yield large scalar perturbations with respect to tensor perturbations, which does not happen in classical models with a single fluid. So our achievements were we obtain a bouncing model with NES close to 1, reasonable amplitudes for bounces between Gaussian and Planck scale, dark energy naturally accommodated. Future challenge is to calculate non-Gaussianities, what happens when you have more than one fluid, entropy perturbations, particle production in the bounce. So to conclude, I think that the Broglie-Bohm quantum theory is very suitable for quantum cosmology. I am advocating, but it's not the only thing, it's not the only way to understand this, but that besides nomological, probabilities are secondary. Now, it explains in a very simple way a very old controversy concerning cosmological perturbation of quantum mechanical origin, the quantum classical transition. And so we had, with basic general relativity and the Broglie-Bohm quantum theory, we had the sensible bouncy model, which can explain the origin of cosmological perturbation in accordance with observations. In such models, inflation can be present, but it's not necessary. And finally, it's a very provocative sentence. It was presented a quantum cosmological model effect with sizable observational consequences, which we have already seen, which is the ratio between tensor perturbation and scalar perturbation being very small. Of course, it's very provocative because there are many other explanations for that, many other. But what I'm trying to emphasize is that this quantum cosmological effect near the bounce made this ratio become very, very small, because scalar perturbations become very much bigger than the tensor perturbations, And this happened just because of the quantum corrections to general relativity. And this is in accordance with observations. Okay? So that's it.
If you start from a classical model, you want to use Bohmian mechanics, which part of classical variable you should leave still classical, how to choose them, and which one you should quantize?
If you want,
you have for example, in phase space you have classical model. You want to quantize it.
Mm-hmm.
Which variables you should leave as a classical? Because a mixture, which one should be taken?
So in this formulation, what is not classical? What is really considered to have objective reality are either positions or amplitude of fields in quantum field theory. So, in some sort, the symmetry in phase space is broken. You see, the symmetry in phase space is broken. So, what has objective reality are positions or amplitudes of fields. These are the things that are real, have objective reality. Then the wave guides the positions or fields.
Mixture of variables is sometimes very difficult to do it. No?
Yeah, you can make a lot of transformations, but in the end you must go back to these variables that you have chosen. Okay. It's, that's it.
So you said that the bounds must be asymmetric, right?
In this example, yes.
Yeah, and so there will be this phase with dark energy and no dark energy phase, right?
Yeah, yeah.
So does it exclude the cyclic cosmologies or cosmologies with more than one bounce?
No, this model doesn't have cyclic situations. So I'm not discussing cyclic models here. Just have just one bounce. Cyclic models, they have something that's difficult because so you have a bounce, and then the perturbations become bigger and bigger and bigger, and then structures are formed, and then if you have a contraction again, then this contraction is not anymore homogeneous. Then this new contraction will produce a lot of black holes. So we have to have a mechanism to erase all the structures that were formed in the expanding phase in order to come back again the same way as before. So people have done this, but you have to put some other fields and so on over here. This bounce that I'm discussing here have only one bounce. And the dark energy effect is only in the expanding phase. So we don't have dark energy
I have a question about the same issue. So presumably there's an initial state corresponding to each of these two possibilities, dark energy in collapse or in expansion. And you still have the superposition principle, right? So you could take a superposition of these two states. And why is that still just one of these two options?
No. No. You can take a wave function which there is either one option or the other option. But you can also construct a wave function with superpositions. Then I don't know what would happen. One thing that is this one? No, I don't think so. The wave function, the situation that we are facing here is that the wave function gives either one situation or another. Maybe superposition, I don't know what will happen, but either one or another. But one thing that we're trying, this situation here, we have dark energy just only in the contacting phases, so we don't have dark energy in the expanding phase. So it's not very interesting, but it can be a good laboratory to see what would be the effect of dark energy in the contracting phase when you can give here, because here you can also give nice initial conditions here, because in the, you can give vacuum initial conditions around here, because this is dust dominated, and then you can give initial conditions here, and as is dust everywhere in the past, so there is not this problem of the enhancement of the perturbations, and then you can see what happens when perturbations pass to a phase of dark energy in the contracting phase to investigate what happens here. But this model doesn't have dark energy in here. So if you take superposition of the two, well, I don't know, perhaps a good thing to investigate.
So that maybe I missed something. These are specific states. Like
Yeah, specific states, yeah. These two pieces are specific states.
I have a more general question about these bouncing cosmologies. So it seems that in order to explain the structure, large scale structure of the universe in the expanding phase, you have to assume a very special state of the universe in the contracting phase. Yes. Whereas in the inflationary paradigm, it is believed that you can start maybe from generic and homogeneous spacetime and produce the structure that you observe.
It can begin with an homogeneous spacetime. No.
So you assume that it is perfectly homogeneous and isotropic in the contracting phase.
Yes, in inflation, this is not true that you can begin with any homogeneous thing and then with inflation, then homogenize it. This is not true at all. In order to homogenize something that's inhomogeneous, then you have some very strict conditions, and you don't have an explanation for. In fact, you don't have an explanation on why the old universe was so homogeneous isotropic. In the case of the bouncing models, what I have in mind is the following. So you have a very big universe, almost flat, very, very big, and just by dissipation of things, like for instance, you have this room, and then you put all the air out around there. So let time pass, then the air will be homogeneous distributed in this room. So we have this very, very large universe of many, many Hubble radius than now, and then it's contracting very, very slowly, and then by the time then we homogenize, and then we have only vacuum fluctuation. But I don't like very much the explanation, but I think it's as good as the explanation that people give for inflation, because really, if you put numerically, if you start with a non-homogeneous space-time, it's not obvious that even with a cosmological constant, you can have an homogeneous space-time. And there are many papers published in the.
It doesn't improve the inflationary
in this
respect.
In this respect, no. I think the problem of why the universe was so homogeneous and isotropic is a mysterious thing. Nobody knows the answer.
Okay.
And just a quick question about the bounce. Does that typically happen at a certain scale, either curvature or a scale factor or something like that, or does it depend on the state?
The bounces that give the good amplitude of the perturbations, they happen when the curvature scale is about 1,000 and 10,000 Planck lengths. Okay, more or less like this. And they must be very, let's say, very steep. No,
okay.
Very steep. So, is that going to go?
And so the curvature scale of the bounce happens, that depends on the state that you choose to start with?
Now, it depends not on the state I choose, it depends more on the initial position of the Bohmian trajectories.
Okay, so you have to choose that curve to get the right. That's good.
Depends on.
Thank you.
Doesn't the value of R depend on some of the initial choices?
For the wave function or for the?
You have to give initial data for all this.
Yeah. No, depends. Okay.